Hi everyone, so in today's video we're going to answer the last question, so supposedly the hardest question from the 2022 Paper 2 Edexcel Pure Maths exam. So this was the Paper 2 Pure Maths from Edexcel, the 2022 exam. So obviously we've got Paper 2 coming up very shortly for both, for all the exam boards, Edexcel, AQA, OCR, so we've got all those Paper 2s coming up very, very soon. So I just thought we would do a Paper 2 question from Edexcel, and then I'll do a Paper 2 question from AQA from the mechanics section in AQA, because in AQA, Paper 2 involves mechanics, but in Paper 2 for Edexcel, it's just pure maths. So we're going to do this pure maths question here, and it's the last question, so the hardest one on this 2022 paper from last year's exam. So let's look at this question here. So Figure 2 shows a sketch of the curve C with these parametric equations here. So we've got parametric equations. We've got T, which is defined between minus pi over 4 and pi over 3. So that's what we have here, the curve there, this curve C. And then we've got this L here, which is the normal line at C at the point P. And at that point specifically here, we've got that T is equal to pi over 4. So just make a note that this is when T is pi over 4 there. Okay, so we've got that point P there. Okay, so using parametric differentiation, show that the equation for the L line, which is the normal line, is this here. So part A of the question wants us to use parametric differentiation. So, I mean, to answer this question, we're going to have to differentiate. We're going to have to differentiate these two parametric equations. So remember, we want to find the equation of the normal line. Remember that the gradient of a normal line is perpendicular to the gradient of the tangent line, and the gradient of the normal line is the negative reciprocal of the gradient of the tangent line. So if we can find the gradient of the tangent line, so our first step is to find the gradient of the tangent line, because if we can find that gradient of our tangent line, this tangent line, I'll try and draw this here, this tangent there, if we can find the gradient of that, then we can take the negative reciprocal to get the gradient of this normal line there. So that's probably how I'm going to start with this one here. So we need to find dy by dx. So firstly, let's find the gradient of that tangent. And remember, dy by dx on a curve is the gradient of the tangent line at that particular point on the curve. So first step is let's find dy by dx. So find dy by dx at t equals pi over 4. So at that coordinate here, this point, at this point P, let's try and find dy by dx, and then we can find the gradient of the normal line. That's going to be our technique. So remember, with parametric equations, just by simple fraction rules, remember that dy by dx is equal to dy by dt divided by dx by dt. So we can differentiate both our parametric equations with respect to t and then divide them by each other. So let's start by finding dy by dt. So dy by dt, so we want to differentiate 2 sec squared t plus 3. Okay, so let's try and do this. So dy by dt is the derivative with respect to time of 2 sec squared t and then plus 3. So I mean, when we differentiate the 3, that just goes to 0. Differentiate a constant gives you 0. So we're just going to differentiate this 2 sec squared t. So this is equal to 2 lots of, so remember, this is just a constant multiplier there. So we can just bring the 2 to the outside. So 2 times the derivative of sec squared t. So how do we differentiate sec squared t? So we're going to need to use our chain rule to do this, because we got this this sec function inserted into this squared function. So this is basically a function of a function. So it's going to be really using the chain rule here. So we're going to differentiate this sec squared t with respect to sec of t. And then we're going to multiply that by the derivative of sec t with respect to t. Okay, so differentiating sec squared t with respect to sec t, well, that's just going to give us 2 lots of sec t. So 2 times by 2 sec t. That's just by, obviously, if you differentiate x squared with respect to x, you get 2x. So differentiating sec squared with respect to sec, you get 2 sec. So it's just by using, it's just using basic differentiation, that first one there. And then differentiating sec. So the derivative of sec, if you don't know the derivative of sec, you could use, for example, you could use the quotient rule, because what sec is, remember, Sec is just the same as 1 over cos t. So you could use the quotient rule to differentiate that if you can't remember the derivative of sec. Now, I can't actually remember, but I think they give you the derivative of sec in the formula book. But if they don't, then you can just use the quotient rule here. So you get 2 times 2, which is 4, and then times by sec t. And then if you do differentiate sec using the quotient rule, if you want to, if you can't remember what the derivative of sec is, so that's going to be the derivative of the top. So differentiating number 1, you get 0, and then times by the bottom v, which is cos t, and then take away the derivative of the bottom times by 1. So 1 times by the derivative of cos, which is minus sines, just put a minus sign. I'm not going to fit it in, minus sine t, that, and then divide that all by the bottom. So when you have your quotient rule, you got u over v. So that's going to be your v squared on the bottom. So your cos squared is going to be on the bottom there. So cos squared t, and then that's all in brackets there. So we get 4 sec t. So 4 sec t. Sorry, let me try my writing neater. 4 sec t, and then times by, so obviously 0 times cos, just 0. That's just 0 there. 0 take away 1 times minus sine t. So minus sine t is a positive sine t. So what we're going to get is sine t over cos squared. Sorry, let me try and rub this out, write this a bit neater. So sine t over cos squared t, and that's going to give us 4 times sec t, and then sine over cos is tan, and 1 over the remaining cos there, because obviously cos squared is cos times cos. Sine over cos is tan. We've got 1 left, 1 cos left over, so we get tan t times by sec t there. And just to make this clearer, in case you're wondering, so remember, sine t over cos squared t is the same as sine t over cos t times 1 over cos t, and 1 over cos is sec. Sine over cos is tan. Sorry, let me just try and box this off a little bit better. So this is a cos there. Sorry, my handwriting is really not good here. That's a cos there. Oh no, the page is frozen again. Sorry, 1 second. Let me just wait for this to sort itself out. There we go. So that's that. Okay, so what we get here is you get 4 sec squared t times by tan t there. So that's our derivative of y with respect to t. Now let's do dx by dt, because we want to do dy by dt divided by dx by dt. Now actually this is a little bit simpler. So we're going to differentiate. So to get the dx by dt, we're going to differentiate 2 tan t plus 1. So dx by dt is equal to the derivative with respect to t of 2 tan t plus 1, which is just the same as, again, very similar to what we did before, 2 lots of d by dt of tan t. Obviously differentiating 1 again is just a constant, so it just gives you 0. Now remember, now this is one that is definitely in your formula book. So differentiating tan will get you sec squared. So you get 2 times sec squared t. So that means that therefore dy by dx is going to be dy by dt divided by this dx by dt that we just got down here. So it's going to be 4 sec squared t tan t, and then divided by this 2 sec squared of t. So that just gives us, so the sec squared actually just cancels out there and there. 4 over 2 is just 2. You get 2 lots of tan t there. So when t is so therefore when t is pi over 4, so remember at this coordinate here, we've got a t value pi over 4. So you just want to plug that in. So we will get dy by dx, when t equals pi over 4 is going to be equal to 2 lots of tan pi over 4, and tan pi over 4 is just a number 1, so you get 2 there. So that means that the gradient of the tangent at P, so grad of tangent at P, is equal to 2. So now then, that means the gradient of the normal line, which is the negative, which has, well, the gradient of a normal line is the negative reciprocal of the gradient of the tangent line. So therefore the gradient, so gradient of normal at this point P, that's going to be equal to the negative reciprocal, so negative reciprocal of 2, which is 1 over 2. Okay, so that means that the equation for this normal line L, so therefore equation for L is going to be y equals negative a half x, and then plus some constant c at the end, which we don't know yet, this y-intercept value. So how are we going to get that y-intercept value? Well, we need to go back to the question. So we know that at this coordinate here, t is equal to pi over 4. So let's actually find out these x and y coordinates. So what is the x coordinate there at P, and what is the y coordinate there at P? And to do that, we can just substitute in t equals pi over 4 into x and into our equation for y. So when t is pi over 4, so when t is pi over 4, our x value is going to be 2 times tan pi over 4 plus 1. So remember, tan pi over 4 is just the number 1. 2 times 1, 2, plus 1 gives us 3. So that x coordinate there is going to be 3. And our y coordinate is going to be 2 times sec squared pi over 4 plus 3. So remember, sec is 1 over cos. So cos pi over 4 is 1 over root 2. So that means that sec pi over 4 is root 2. So sec squared, so let me just write this here just to be very clear. So cos pi over 4 is equal to 1 over root 2. So that means that sec pi over 4 is equal to root 2. So that means that sec squared pi over 4 is the square of root 2, which is 2. So you've got 2 times 2 plus 3. 2 times 2 is 4, plus 3 is 7, that's 7 there. So you've got a y coordinate of 7. So the point P, so we know the coordinates of this point P must be 3 and 7. So I'll just write this here. So P is 3 and 7. Okay, so now we can plug this back into our gradient of our normal line. So the gradient of the this equation here. So we're now going to just plug in, so plug x equals 3, y equals 7 to work out this y-intercept value, this plus c. So you get 7 equals minus a half times 3 plus c. So therefore we get 7 equals minus 1.5 plus c. So therefore c is going to be 8.5. We just add the 1.5 to both sides. And that's the same as 17 over 2. So therefore the line L is going to be y equals negative a half x, and then plus 17 over 2. That should be a 2 there. And if we just check the question, yeah, that's exactly the same equation that they got there. So that's how we would do that one. And just to emphasize again, this thing that I wrote over here, because I don't think I did this very well. Let me just try and write this out again in case you were confused at this step. So what I just did here to differentiate the 1 over cos is use the quotient rule. I mean, actually, I'm pretty sure this is in your formula book. I mean, I've not got my formula book nearby with me right now, so I can't remember exactly what is in the formula book, but I'm pretty sure that the derivative of sec is in your formula book. But what I just did here is use the quotient rule. And in fact, let me just, I want to be really clear, and I want to make sure I give you a full proper answer rather than just rushing my work. So I'm just going to go back and redo this a little bit. So I've used the quotient rule here with my u equal to 1, my v equal to cos t, and then what I did here was using my quotient rule formula, differentiate the u, so differentiate 1, you get 0, so you're going to get 0 there, and then times by the bottom, which is cos, but 0 times cos is just 0 anyway, and then you're going to take away the derivative, well, you're going to take away the top u, this u, which is your 1 there, so your u in your quotient rule formula is 1, your v would be your cos t in your quotient rule formula. So when I say u and v, I'm talking about that quotient rule formula involving u and v. So you've got 1 and then times by the derivative of cos, which is minus sine t. So so this is so this dot here means times. If I ever write a dot, it means times. So hopefully you've seen that in class, but a dot in maths just means times. So actually I'll just make this clear if you've not seen this before. This is a times sign. So minus 1 times minus sine is positive sine. So that's where I've got this sine over cos squared from. And again, just to emphasize this, sine t over cos squared t is the same as sine t over cos t times by 1 over cos t. And sine over cos is tan. That's where I've got this tan there from. And 1 over cos is sec by definition. That's where I got the sec from there. So I just wanted to go back to that, just in case you weren't sure about what I did there, just because I want to make sure you all understand that perfectly. But that's the first part of the question done there. So on part A, that's all good. Part B, so show that all the points on the curve C satisfy the following equations. This equation there, so y equals a half of x minus 1 all squared plus 5. So I'm just going to write out our parametric equations again. So for part B of the question, we've got our parametric equation. So x equals 2 tan t plus 1. And then we've got y equals 2 sec squared t plus 3. I'll just make sure I've got the right numbers again. Yeah, they're the right numbers. Okay, right. So we want to basically get the Cartesian equation. That's what the question wants us to do. It wants us to get the Cartesian equation for the curve. Okay, so we want a y equals formula. So I'm looking at this. I want to get a formula for the curve y equals something in terms of x. Now, I know when I look at this x formula, I've got a tan there. And I know when I look at this y formula, I've got a sec squared there. So I'm thinking, right, how can I try and change this this formula for y involving this sec squared into tan? And I remember my identities because I know my trig identities, and hopefully you do as well. And I know this trig identity. So I know that 1 plus tan squared t is equal to sec squared t. So what I'm going to do, instead of having a sec squared t there, is I'm going to write 1 plus tan squared instead. Because again, I noticed that in my x formula, my formula for the x coordinate, I've got a tan involved. I've got a sec squared involved there. So I want to get rid of this sec squared and write it in terms of a tan instead, because that's going to help me get a Cartesian equation. It's going to help me eliminate this variable t to get the Cartesian equation just in terms of y's and x's. So let's just plug this in. So using both these facts here, I've got y equals 2 lots of 1 plus tan squared t, and then plus the 3 at the end there. Okay, so we've got, just by expanding the brackets there and there, we've got 2 plus 2 tan squared t, and then plus 3. And then 2 plus 3 is 5, so we're just going to write this here. So we've got 2 tan squared t plus 5. Okay, so now then, we're nearly there. I've got this tan squared involved, this tan squared t involved in my formula. Obviously, I want to get rid of this tan t. I want to eliminate the variable t in place of the variable x. So now I can use this x formula up here. So let's make tan t the subject of that formula. So remember, we've got the x formula, x equals 2 lots of tan t plus 1. So I'm just recopying out this again. Let's make tan t the subject of the formula. So we're going to take away 1 from both sides. We're going to divide both sides by 2, and we get that tan t is equal to x take away 1 over 2. So take away 1 from both sides, divide both sides by 2, we get that there. So now I'm going to plug this into this formula here. So therefore we get y equals 2 times by tan squared. Well, that's just going to be this, isn't it? So x minus 1 over 2 all squared, and then plus 5 at the end there. So, I mean, if we just go back to the question and see the format that the question wants us to have it in. So it's a half times x minus 1 all squared at plus 5 at the end. So yeah, we're nearly there. So what we just want to do now is we want to say, okay, so this is 2 times by x minus 1 all squared over 2 times 2, which is 4. So I'm just squaring the top with a fraction, squaring the bottom to get this there, then plus 5. And obviously 2 over 4 is a half anyway, so we get half times x minus 1 all squared plus 5, and y equals that. So that would be our Cartesian equation, and that is exactly the same as what the question wants us. So all the points on the curve do satisfy this equation there. So we've done that part as well. Okay, so then the next part, so the straight line with the equation y equals negative a half x plus k, where k is a constant, intersects at 2 distinct points on the curve C. Find the range of k values. Okay, right, so we've got this this line with a gradient negative half. So actually a line which is basically which has the same gradient as this normal line here. So parallel to this normal line here. So let me just actually, I'm going to just rub out this mess here just to just because we've done this now, so we're happy with all this stuff here. So I'm going to rub out this tangent line here. So what we've got is we've got this like family of curves, this like family of straight lines. So we got that there, that there, that there, that there. So we got these red lines here which have a gradient of negative half parallel to this like normal line that we found in part 8 of the question. These lines all have a gradient of negative half, and we've got this like plus k at the end here, and we want to find the values of plus k that give us two distinct points of intersection. So for example here, whatever this y-intercept value there is, whatever that k value is there, that gives us 2 points of intersection, as we can see there. But for example, this k value up there, this y-intercept there, with this straight line with the gradient at negative half, only, well, it gives us no points of intersection. But this one here gives us 1 point of intersection. So we want to find the point that the k value, the y-intercept value for this graph with the equation y equals negative half x plus k, the k value, the y-intercept value that gives us two distinct points of intersection. That's what we're trying to find in this question here. So essentially what we want to do is we want to set this equation there, this y equals negative half x plus k, equal to this Cartesian equation. But we just got to be careful, because this equation here, yes, it is the Cartesian equation, but obviously this full equation for all x values is not the actual equation of the curve C, because remember we've got this stipulation here that t must be between minus pi over 4 and pi over 3. So what I'm going to do first is just try and find the domain of x values. So we need to find the domain of x values. So we do that by plugging in minus pi over 4 into our x function, and t equals pi over 3 into our x function as well. Because remember, and again, I'm just going to rub out these red lines again, just because I'm making a bit of a mess with this. So remember, this curve is only defined between this x value there, so this like value there, and this value there. So it's only x values in this domain of values there, because that's where the curve's defined. The parametric equations are only defined when t is between minus pi over 4 and pi over 3. So they're not defined for all t values. So they're not defined for all x values in the real numbers, so all numbers on the x-axis. They're only defined between these two numbers there. So we need to actually find out what these two numbers are, so our domain of x values. And then we can set this equation here equal to this Cartesian equation, and then we can try and determine what the k values could be. Okay, so let's try and do this then. So let's find our domain. So so part C. So again, we've got this the x values are defined by 2 tan t plus 1, 2 tan t plus 1. So I'm just going to plug in t equals minus pi over 4. So that was our lowest t value possible. Again, if we go back to the question, that's our lowest t value possible. So I'm just going to plug that into my equation, and I get x equals 2 times tan minus pi over 4 plus 1. Now, tan and minus pi over 4 is actually minus 1. So we've got 2 times minus 1 plus 1. That's going to give us minus 1. So minus 2 plus 1 is minus 1. Now, if you plug in t equals pi over 3, so we're going to get x equals 2 times tan pi over 3 plus 1. Now, tan pi over 3 is root 3. So you've got 2 root 3 plus 1, so 2 root 3 plus 1. So what we know there for them, I'm actually running out of room on this paper, but the domains, we know that the domain for the curve C is x between, so x in the set of values between minus 1 and 2 root 3 plus 1. So that's our domain of x values. So we'll just keep this in mind. So what we're going to do now is we got the Cartesian equation for the curve defined between x equals minus 1 and x equals 2 root 3 plus 1. So this is the curve C for these particular x values here. And then we've got this new straight line with this equation back here. So minus half x plus k. and we're going to set these two equations equal. So what we're going to do is set this expression equal to this expression to find the points of intersection in terms of k. So we're going to do, and in fact, I'm going to go to a whiteboard using my my Zoom application. Let me just do this now. Okay, so we've got the Cartesian equation, half. Sorry, let me do that again. So half of x minus 1 all squared plus 5, and that's going to be equal to our linear equation, so this negative half x plus k. So we've got the line there equal to this there, and remember our domain of x values, let's just put it in a box here, that our domain, so domain is x in the set of values between -1 and 2 root 3, sorry, 2 root 3 plus 1. Okay, right, so now then let's try and get a quadratic equation and rearrange this. So we've got a half, so therefore we've got half, and then times by expanding the brackets inside there, we'll get x times x, x squared, x times -1 minus x, and then plus another minus x, we get minus 2x, and then -1 times -1 plus 1 at the end there, and then plus 5, and that's going to be equal to negative a half x plus k. Okay, so we've got expanding the brackets here, so we've got half x squared minus x plus a half plus 5 equals negative a half x plus k, and then just rearranging this to get everything to one side equal to 0. So if we do this, we get half x squared. If we add the half x to both sides, this half x to both sides, we get negative, so negative a half x, and then a half plus 5, that's going to be 11 over 2. So we've got plus 11 over 2, and then we're going to take away this k from both sides. We're going to take away k there, and then that's equal to 0. Okay, so we've got this quadratic. In fact, I'm just going to times everything by 2 to get rid of these fractions here, just to make the equation look a bit nicer. So we've got x squared minus x plus 11 minus 2k, because we've got to times that by 2 as well, and that's equal to 0. Okay, so we've got this. Now then, we're going to need to use our discriminants. Remember, we need the discriminant now, don't we? Because we want there to be two distinct solutions. So if we go back to the question just to remind ourselves, let's go back to the question. So we want there to be two distinct points of intersection between the Cartesian equation here and this straight line equation. So we need the discriminant b squared minus 4ac to be greater than 0. So remember, in our quadratic formula, we have our discriminant. So we'll just do this in red over here. So let me just put a box around here. I've made a real mess of this question, haven't I? So remember our discriminant. So discriminant is the part under the square root in our quadratic equation. So b squared minus 4ac. We need that to be greater than 0 for two distinct roots. And that's what we're looking for with this equation here. We want two distinct points of intersection, so we want two distinct roots. Okay, so therefore we need b squared minus 4ac, so b squared minus 4ac. So our b is going to be this -1 here. Let's just make a note of this, that b with this quadratic equation here is the coefficient of x, so -1. The a is going to be 1, the 1 in front of the x squared there, so a is 1. And then our c value is going to be the constant, this 11 minus 2k. So c is 11 minus 2k. Okay, so we've got, in our discriminant, we've got 1, because 1 squared is just 1. And then take, well, sorry, -1 squared. Yeah, so -1 squared, let me just emphasize this. -1 squared, that's just going to be 1. And then we got 4 times by a, which is 1, and times by 11 minus 2k. This must be greater than 0. Okay, so now then what we've got, so we got 1 and then -4 times 11 minus 2k. It's got to be greater than 0. Okay, so now then, let's just make my writing smaller so we can fit this all in. Okay, so we've got 1 minus, so 4 times 11, that's going to be -44. -4 times 2k, that's going to be plus 8k. It's got to be greater than 0. So therefore, if we just rearrange all of this. So we got 1 minus 44, which is minus 43, plus 8k must be bigger than 0. So therefore, 8k must be greater than, it's got to be greater than 43. And so therefore, k has got to be bigger than, 43 over 8. Now, again, this is not actually going to be our final answer. So, I mean, if this parametric equations, the curve that we have, this curve C, was defined for all x values, every single x value on the number line, then yeah, k would be k could be bigger than 43 over 8. But that's not the case because, remember, as we said before, this curve is only defined for t values between minus pi over 4 and pi over 3. So it's only defined in this domain there. So it's only defined when x is between, as we said before, minus 1, so like this minus 1 there, and this 2 plus root 3 there. So it's only defined in this domain of values there. So what we're going to have to do is we're going to have to find this point. They're going to have to find this point there. We're going to have to find the gradient, sorry, not the gradient, sorry. We know the gradient's got to be negative a half because it's got to be parallel to this normal line there. We've got to find this k value there, that k value there, such that this intersects with this coordinate there, this y coordinate of 7, and this other point there. So we've got to find out what that k value would be. And we can actually do that pretty simply. So we know that the equation of this red line here that I've drew in is y equals negative a half, because again, that's what the question wants. The equation of this line must have a gradient of negative a half. So we've got y equals negative a half x plus k. I'm just going to call this capital K just to distinguish this between the general K that we had before. So we want to find out this K value that intersects at this coordinate minus 1 and 7, and also this point down here, which we don't know, which we don't actually need to know anyway in the first place. So let's try and find out what that would be. Actually, sorry, wait, is this coordinate going to be minus 7? Sorry, my bad, this is wrong. Sorry, forget this. That would not be minus 7. Sorry, my bad, because this is the coordinate point P, not the coordinate of this y value there. So we need to find out the coordinate of this y value here. Sorry, my bad. So the y value there at this point there. So y is going to be equal to what we get when we plug in x equals minus 1 into our Cartesian equation. So we just sub in x equals minus 1. So sub x equals minus 1 into that. We get y equals, so a half times minus 1 squared plus 5. So minus 1 take away 1 is minus 2. Minus 2 all squared gives us 4. Half 4 is 2. That gives us 7. So in fact, actually was 7. So yeah, this y coordinate there is going to be 7. So y equals 7 there. Okay, so what we're going to do is we're going to again, take this y equals negative half x plus k. We just go back to the whiteboard. I'll go to a new page for this. So I'm just going to roughly draw out a sketch of the curve again. So you've got this curve like this. You've got the coordinate there, minus 1. You've got 7 there. And we want to find the equation of this straight line there. So remember, this is y equals negative half x plus k, where this is this k value there, that y-intercept value there. And we know that the coordinate minus 1 and 7 lies on this. So we just substitute in x equals minus 1, y equals 7 into that. We get 7 equals minus a half times minus 1 plus k. So therefore, what that means is that k is going to be equal to, so 7, and then take away half. So half times minus 1, negative half times minus 1 gives you positive half. So you get 7 equals a half plus k. So therefore, that means that k is going to be equal to 7 take away half, which is 6.5, which is 13 over 2. So this k value there is going to be 13 over 2. Okay, so we now know that, so we now know the following. Sorry, let me just move this up again. So we've got this curve here, this equation there, which is y equals negative half x, and then plus 13 over 2. Using our discriminant, what we did with the discriminant, we said that k must be bigger than 43 over 8. So what that means is that, well, what we've just essentially worked out, again, if I try and draw like a new curve to explain this better, so we've got our curve like this. What we just worked out with our discriminant calculation is that k must be bigger than 43 over 8. So it's got to be bigger than that number there. So if we draw like a tangent at this point here, so this is y equals negative half x. So this equation with the gradient of negative half, which is just touching, which is tangent to this curve, our curve C there. So this, I'll just do it in red actually. This is our curve C with our parametric defined by our parametric equations. This is our curve C. So this straight line with a gradient of negative half touching tangent to this point there is y equals negative a half x, and then plus this 43 over 8. And that's because of what we did with our discriminant. We worked out that k must be bigger than 43 over 8 in order for there to be two distinct solutions. But what we just did back here in this calculation is we said, well, okay, well, the curve, obviously, again, this curve C is only trapped between -1 and 2 plus root 3. It's trapped between those two values. It doesn't go beyond those two values. So it doesn't go up like this, like a normal quadratic, because the parametric equations are only defined by these values here. So what we're saying is that we've got this brand new line that we need to draw in here, like this. So this other line, this green line, which is y equals negative a half x. And then what we just worked out was that this is plus k, which is 13 over 2 there. So that's telling us that the curve will have two distinct solutions when k is between 43 over 8, so this 43 over 8 value there, and this 13 over 2 value there. So it can also, well, it can be equal to 13 over 2, because that gives us two distinct solutions when k is 13 over 2. So when this is 13 over 2, when our y-intercept is 13 over 2, we get two distinct solutions. When our y-intercept is this 43 over 8, we only get one solution. So that means that therefore k must be greater than, so the k value has got to be greater than 43 over 8. So strictly greater than to give us two solutions, but it can be equal to this 13 over 2 because if k is equal to 13 over 2, we get two solutions there and there on our curve. So that would be our final answer to this question here. So hopefully I've explained that well enough. I mean, it was quite a tough question, but the idea with this one is that you want to use your discriminant to find out what your k value is here on this straight line with the gradient of negative half, which is going to give you this one point of intersection. So using your discriminant, you can find out the k values, what your k values need to be in order to give you 2 points of intersection with the curve, between the straight line and the curve. But because we've got a fixed domain, a fixed subset of the real numbers, so our domain is not everything on the number line, it's trapped between -1 and 2 plus root 3, we actually have to look at our curve and say, well, okay, well, k, yes, k must be bigger than 43 over 8 because our discriminant told us that, but actually it's got to be less than 13 over 2 because the curve stops here. The curve stops at x equals -1 and y equals 7. And because it does that, it means that if we had k values bigger than 13 over 2, look what would happen. We only get 1 point of intersection there. So, I mean, if this curve continued forever like that, yeah, we would get 2 points of intersection, but the curve is defined such that it stops here. So actually, we would only get 1 point of intersection if k is bigger than 13 over 2. So k must be between 43 over 8, but strictly bigger than 43 over 8, and it must be less than or equal to 13 over 2. And that will give us two distinct solutions, two distinct points of intersection between the curve C from our parametric equations and this y equals -1/2 x plus k value. So any questions, please do drop them in the comment section. Again, quite a tough question, but hopefully that all made sense with this question there. So yeah, if you are an Edexcel student, good luck for your paper 2 exam. Any questions, put them in the comment section. And if you do want some support, remember, you can email me. I do charge to answer your questions, unfortunately, but you can email me, Dr. Differentiation, Dr. Differen. Sorry, let me just be clearer. T-I-T-I-O-N at gmail.com. So do email me, doctordifferentiation@gmail.com, and I do charge to answer your question. So if it's just a brief question, it'll be £1 or £2 to answer your question. If it's a longer question, I charge £1 per mark to help you answer a question. But please do get in touch if you need any help. Thanks a lot for watching today's video, and again, good luck for your paper 2 exam for you Edexcel students.